before I start the lecture, I want to start with an exercise with constructing algebraic structures. So, in the video where I talked about the Femboy donut, right? What we did was given some axes, right? So we have this axis here, and then we have this point and this point, and then so we have this box here. Goes this way, it's that way. Just so that we have some orientation on our manifold. What we did was attach these 2 points together, or bring them together and glue them, topologically speaking, to get a cylinder. And so these two stay pretty much the same, but these two are connected, and then they become this one point here in the middle. They become this one point here. So we set this equal to this, and then we get a cylinder. And then what we did to the cylinder is we bring these two together, or these two circles, and then just bring them or attach them around, or bring them around to attach them, and we get ourselves a donut. Or torus. And then of course we have ourselves here that these two are equal now. And then we have a point. We have a point that's running all the way around the torus. So, and then that's running this way. And I specified that, I specified what this is. This is the quotient group between the complex numbers and the Gaussian integers. But I failed to specify what this is. This over here, this box here, is just the interval 0, 1 cross itself. That's it. This is this box. That's it. It's just closed interval from 0 to 1, taken with its direct or Cartesian product, topological product, I mean, with itself to get this box. And so to obtain this, I actually neglected to mention what the cylinder is. And what the cylinder is basically S1 cross our unit interval, which our unit interval is, of course, 0, 1. Now, this is another reason why in topology we do not use I to denote an index set. That's why we use J to denote an index set. Because when we use I, or when we say I, we mean the unit interval, which is the interval running from 0 up to 1. And so this is a cylinder over here. And what is cool about it is that, notice how, where's the eraser? Notice how when we have a regular circle, S1, when we say Cartesian product, what we mean is we attach one point to another point. So given a point over here, x, taking our Cartesian product between x and another point y, or so, well, x in x, and another point, we'll say y, or a height, let's say, y in y, we say that the point wherein they coincide or they intersect, let's say for example this point here, which I will call xy, is inside the topological product between x and y, or rather the Cartesian product. We bring them together into one unified point. Now, one other thing that I need to say or discuss about FT2, or FT2. So we have our Femboy donut. What we mean by FT2, which is the Cartesian product between two S2s, so F_S2 cross F_S2. What we mean by this is that for every circle or Femboy circle, Fs2, each point is attached with another circle, or there's a circle attached to each point here. This is our second Fs2. And since we're taking the total Cartesian product of this That means we are attaching circles to every point here. So we're just attaching circles, and then so on and so forth. And as you may notice, if we make it finer and finer, our collection, it essentially is isomorphic to R. Or rather, homeomorphic to R. Since it's homeomorphic to R, it's a manifold. And of course, the thing that this closely resembles is a torus. If we take finer and finer products of FS2 with itself, we have ourselves a torus. That's why FS2 cross FS2 gives us a torus. Because for every circle, small circle, we attach it onto every point here on this big circle. And so essentially this circle, this original FS2 that we attach points onto, becomes a new, the inside part of our femboy donut. So now, what we want to do is, as a small, abstract algebra exercise, is attempt to construct a paddle wheel. Now, what is a paddle wheel? A paddle wheel is like I would say another version of the gear. I have a paper on what the gear is. You guys can check it out. I think I'll link it, or you guys can just check my my Femboy Mathematics channel to see it, because I posted the video about it there. Gist of it is that a gear is some is a construction over a mathematical structure such that multiple elements actually map onto one element, and that one element maps onto two elements, and that pair is mapped onto another pair. So we have some basis element E, not Euler's number, which is mapped onto two elements, say A1 and A3. And A1 and A3 are mapped onto the respective elements A2 and A4. And after that, these two actually wrap back onto E. And this is the most trivial version of the gear. You can define multiple basis elements, such as E1, and then make some E2. But essentially, with most examples, such as, extending the ring, R plus and dot, or constructing a gear over it, when we unfold a gear over the ring R plus and dot, we actually want that E1 is equal to E2. Because when we specify our gears, and essentially take their union, in order to decompose this, right? So that we account both addition and multiplication operations. We need it such that we only have one multiplicative and additive identity element. And that would be either 0 for the plus and 1 for the multiplication. So that's just a gear. And how the heck does that apply to linear algebra? This next thing that I'm going to construct? Well, actually, it doesn't. That's the surprising thing. It has nothing to do with this. The paddle wheel has nothing to do with the gear. Or actually, maybe you guys can make some sort of correlation and say that, it could be the box that we attach to the cylinder, or other let's say the paddles, or the squares that we attach to the cylinder are actually could be the teeth of the gear. That A1, A2, A3, A4 thing can actually be that. But I'll make that correlation right after I make this construction. So let's take a regular circle, S1. You guys know that. Now, what we want to do is take its Cartesian product with the unit interval 0, 1, which is just I. So S1 cross I. Take it. So with that, we have multiple lines running through here. And So we have essentially a cylinder. Okay, so we have a cylinder. This is S1 cross I. So next, what we want to do is have some, well, let's have a small axis over here. Just a small axis. And it could be any, I could say L cross L. Any space. And then pick a small thing here. So let's say this is the origin is E over here. Okay? And this is say a Y, AX. So now what we want to do to make this, to extract this box, is say, oh well, let's just take the topological product between the interval E up to AY cross E up to AX. Close, of course. When we take this product, it's essentially this square over here. We have ourselves a square. With this point being E, this point being AY, this point being AX, and then this point being AY, AX. Oh, sorry, this is a pair, not really interval. Yeah, that's kind of the ambiguous part of mathematics. You can actually confuse an interval with an ordered pair. Okay, but I think there's some technique that sort of removes the ambiguity of it all. Okay, so now what we want to do is attach this onto our cylinder. Now, I want to make things specific by saying, oh, well, instead of just thinking of this as some long length, let's shorten it. Let's shorten it to the length EAX. Let's shorten it to the length EAX. Let's say that that's the case. Let's say instead that this cylinder is EAX long. So that means we now have some, this is our square now. So what we do next is take the product between this, which I will call Q, with our given cylinder. And so what this tells us is that for every point or every plane here, we attach a square onto it. So essentially, we have ourselves our paddle wheel. And I know there's supposed to be like a lot of points here, or a lot of planes or squares right now, but just bear with me when I draw these things, because it's a bit hard to draw these things and make the picture. So there we have it, a paddle wheel, something that's similar to a gear, aesthetically saying, but it's essentially something else. And so we made some relation between an actual gear and this physical mathematical object, or rather aesthetic kind of gear, which is a paddle wheel. So yeah, speaking of cylinders, actually, in tangent bundles, we're going to be talking about Riemannian manifolds. More specifically, our application of it, which is the FR-Manifold. The FR-Manifold. FR. And this is not the for real that you guys hear a lot on the internet. What we mean in Femboy theory, what we mean by the FR-Manifold is that it is what we call the Femboy Riemannian Manifold. So FR or FR is just a small abbreviation for Femboy Riemannian. So if you want to be very fancy about it, you can call it the Femboyic Riemannian Manifold. But we just call it the FR-Manifold, or just the regular Femboy Riemannian Manifold. And to discuss Femboy Riemannian manifolds, we need to first discuss about actual Riemannian manifolds. Okay? So the first thing you guys need to know are tangent spaces. Now you guys know what a vector space is, right? Vector spaces are just sets of vectors, a collection of vectors. Now tangent space, think of tangent space as a generalization of tangent vectors. So given a curve, so given a one-dimensional manifold embedded in some three-dimensional differentiable manifold, let's say this is some f of x inside R2. Now we know that R2 is, we don't need to worry about R2 because we know that R2 is differentiable already. It's differentiable at all points considering that our function is not asymptotic. So when we want to say, oh well, let's disregard 1 over x for now, or such functions wherein we would get some indeterminate form, okay? So what I want to do is extract the function 1 over x, or any rational function, such that an input would give us an infinity. So it has to also be compact. So I want to say that R2 minus the point 0, we're not going to talk about this because a Riemannian manifold must be compact too, which means all intervals are closed. Or, well, you can construct open intervals in it, but then ultimately the set itself is purely a closed interval from 0 running to infinity. Of course, infinity is not included, but given a point in infinity or at infinity, we could construct a closed subset every time. So that's the most elementary definition of compactness of a manifold or topological space. Now, okay, let's consider f of x and consider its derivative. Okay, when we consider its derivative at a point, you guys think about tangent lines, thinking about well, rate of change based on your physics or your basic calculus. And so now let's take a different perspective and say, well, let's say at this point over here, you know this is a minimum, right? Think a tangent vector. So now think of the derivative at a point, well, let's call this A. Think of this as, well, f prime of A. So this is a derivative at that point. Now, instead of thinking of it as just a tangent line, think of it as a velocity vector. So if we think of f of x as sort of the position function of, say, a particle or an object, a derivative at a point would most definitely be its velocity. And so the derivative of the derivative is the acceleration, the derivative of the acceleration is the jerk, and then so on and so forth with your physics terms. So this is what is called a tangent vector. Okay? And so this is an element of what is called the tangent space of this function, well, at the point A. So now let's take another example of a tangent space. So let's take the most trivial example, S1. Yes, we keep returning to S1 all the time. The thing is, it's the most simplest thing to work with. Now this is S1, a circle. And then say we have a point A over here, of course included. A. So our tangent space, our tangent space for this manifold, this two manifold, no, not two manifold, one manifold I mean, is this over here. This plane that extends, or this line that extends so. So if we're given some vector, right, running from here onto here, say vector v, we say that the tangent space of S1, which we'll call, excuse me, T, the tangent space at A of S1 is the span of V. So the span of V is basically just the line that runs across it. So all vectors that can essentially be expressed as a linear combination of V with itself, or not really linear combination, but rather linearly dependent vectors with V. So essentially vectors that stay in the same line as V. And all those vectors are essentially the tangent space of S1 at the point A. Really simple concept. Now for a sphere, say S2. let's say S2. Okay, how about S2? Is a three-dimensional shell, let's say. Now, for that, since it's a three-dimensional object, so I'll specify it here. And this is our center. Now, our tangent space would be a plane, wherein we have two basis vectors which specify exactly where. And so this is our point A now. And so there is some stuff like you need to actually specify the cosines and sines of these two basis vectors to specify more what else you're saying. And we also need to consider some contours here, and then also sort of shifting between two contours. That's a happy face. Okay, so yeah. Aside that, well, that's essentially the concept of a tangent space. A tangent space is like a vector space, but it contains only all possible tangent vectors at a point on a manifold. So all possible vectors right here. So given some curve, I'd say, given some curve, which I will call S, or well, it's called phi, that maps the interval -1 to 1, or -1, 1 onto R. And given some minimum, or this is a curve. This is our f of x, and given some point A at phi, or the derivative of phi. Oh, well, we have some. Okay, I'm gonna specify more. We're gonna map phi onto its derivative. Okay, so we have some b phi that maps phi onto its derivative. So now, this derivative phi prime evaluated at A gives us a tangent vector. Now, partial if phi is some multi-dimensional function, like let's say it has two coordinates, let's say, okay? So there are two directions where we have to consider. Definitely use the partial derivative, or take the partial derivative with respect to x, and then the partial derivative with respect to y. Or your second independent variable. And then evaluate those at the point A. All possible evaluations on A would give us tangent space. Okay, now we discussed the tangent space. What we want to do next is discuss tangent bundles. Now, tangent bundles are a relatively simple concept. If a tangent space is a set of all tangent vectors, a tangent bundle now, or actually just in general, a bundle is a collection of tangent spaces, or a bundle, as we generalize it, is a collection of spaces. So actually, when I say, or when I talk about abelian blocks in person theory, or well here actually, and talk about collections of let's say spaces, or Bussy spaces, let's say, that's actually a Bussy bundle. It's a bundle. And so, formally speaking, given some P, so tangent space at the point X of a manifold M, well, we want to say that M is differentiable, so that we can take the tangent vector at X, okay? So that we can determine the tangent space at X. M must be differentiable at X. And all points, actually. Better if X is, it's better if M is differentiable at all points, or is just, a differentiable manifold, such as R2. So we can, when we say that it's differentiable, actually, I neglected to mention this. When we say it's differentiable, that means we can perform a calculus over it, which means we can apply our techniques of calculus on here. So we can make a curve inside it, and then we can find the derivative of the curve, we can find the integral of the curve, we can apply the intermediate value theorem on that curve, we can find its minimum and maximum. So that's that. That's a manifold that's differentiable. Okay, so given this over here, the tangent bundle of M, which is just Tm, is equal to the disjoint union of the tangent spaces of M. So X in M. So this is just basically the disjoint union, which means we basically join together every possible tangent space in M at the point X, or at all points actually, maybe, perhaps. And then we just put them together without intersecting them. So an example of tangent bundle would be the cylinder actually. S1, this is why I want to discuss about this. S1 cross I is a tangent bundle. Because notice how when we have a circle, S1, we attach notice how we attach every point with a line. And notice how this is actually normal or tangent to the circle. And so that's why this is actually a tangent bundle, because when we attach each point with some line, we end up with a cylinder. And each line is actually tangent to S1 over here. So essentially we have a tangent bundle. So that's why I wanted to discuss it actually. That's the reason why I wanted to connect that, because this is actually an example of a tangent bundle. And so yeah, this is just a disjoint union of every tangent space over M. Okay. So how the heck do we apply these last two concepts in the concept or in our study of femboys, right? So what I want you to consider is that instead of, right, we have some femboy manifold, Fm, okay? So we have some Fm. But let's say the Fm is differentiable at all points, so we can find sort of the direction of where femboy is going, right? By taking just a derivative of a given curve, or given function on that manifold at one point. Now, we can construct some femboy tangent space by basically taking all possible tangent vectors, or tangent femboys at a point, on the derivative of the function or the curve in that manifold, or that Fm, basically. And so, yeah, actually, astoundingly, or quite surprisingly, actually, vector fields are a section, or is actually a subset of tangent bundles. Because notice how, well, we're signing each point here with a tangent vector, right? We're signing each point here with a vector. So that means that's essentially the concept of a vector field. This is essentially a vector field. In fact, formally speaking, a vector field is a section, so-called a section of a tangent bundle. Yeah, actually, it's actually quite coincidental, and it's actually very, very beautiful that we can actually generalize the concept of a vector field as a part of a tangent bundle. So yeah, that's actually pretty cool. So now that we've talked about this, tangent bundles, tangent spaces, let's talk about the Riemannian manifold, or our FR-Manifolds. FR-Manifolds, or Femboy Riemannian manifolds. Now, now that you guys know what tangent bundles and tangent spaces are, let's define a new metric, which is G. I wanna make a new metric. Let's construct a new metric G, wherein in G there exists some G phi or GP, or so. Okay, given some manifold M. Okay, we have some manifold M, differentiable, and then its boundary. Okay, make some metric GP that maps the Cartesian product, or rather the direct product, I believe, between the tangent space of M at the point P cross itself. So two inputs from the tangent space, so two vectors, and sends them onto R. So this takes two vectors, and then given those two vectors, we get some real number. Probably the distance, probably the, maybe the dot product, perhaps, of the two, or not the cross product, but rather the dot product, I believe. And so, which has a norm. A norm. So the norm is defined like this. So dot norm dot at the point P maps one input, a vector, inside the tangent space of M, and it maps it onto R. That's one. And so it's defined by this. So given a vector V at the point P, its norm is equal to the square root of G, the point P, VV. So V with itself. And actually, an example of this function is actually just the norm of the vector, or the length of the vector. So, you know from physics or your linear algebra that the norm of V is equal to the square root, of x squared plus y squared, where in x squared, x and y are the Cartesian coordinates of the vector V. And in fact, this x squared, y squared is this GP of V and V. And actually, this defines, this metric GP defines the components of our vector. So it takes two vectors here, or rather the vector in itself, and it sends it to R. So it gives us, it corresponds R with a part. So it gives us an x and a y for the vector. Now, okay. So now, let's say that M is some F manifold. So let's say that this M is an Fm. And this is our boundary of the Fm. Now, replace R with F. And then just replace R with F. And then we have some point, and then this is called Fm, obviously. Okay, now we have essentially applied it on our theory. So now, given some Femboy manifold over here with its boundary, we have ourselves a Riemannian metric over it. This is called a Riemannian metric, by the way, that maps two vector femboys inside this tangent space, vector femboy tangent space onto F, right? And it gives us some. It tells us the components of the femboy, right? What they're composed of, essentially. And so now, just equip this Femboy manifold with this Riemannian metric. This entire thing is just denoted as G. Just equip G with this, and we have ourselves a FR-Manifold. Our FR-Manifold. Are you for real, professor? Because I am for real. So now, now, let's say that, well, Fm, well, let's just assume that this is the manifold itself with its boundary, okay? Well, it's equal to itself, Fm with its boundary. This over here, Fm, equipped with G, is a Femboy Riemannian manifold. And there, our work is done in constructing this thing. Relatively easy thing to construct if you know about tangent spaces and tangent bundles. But yeah, this is our FR-Manifold. just basically a smooth, differentiable F-manifold equipped with our Riemannian metric. Now, an important thing is that, well, the manifold or the Femboy manifold must be differentiable at all points. We cannot have undefined points or indeterminate points that have that yield indeterminate forms given some functions. Of course, we're not going to extract every point, but we won't have all curves. Okay. I mean, of course, we can accept some curves. We can definitely accept 1 over x, but as long as we're able to do a calculus over it, or as long as we're able to do calculus in it with its numbers and stuff like that, we have no problems with it being a differentiable manifold, and thus, well, being a Riemannian manifold. An example of a Riemannian manifold is R2, actually. Real numbers. You guys know that calculus is actually happens within a Riemannian manifold, which is R2. Because it's smooth, it's also compact, I would say. Well, there are some sections of R that aren't compact, but of course, overall, it is compact. Right? Actually, I don't think it is, but rather, we can still perform calculus over it, and we can still construct compact intervals within it. Okay, so that's what matters. For me, it doesn't quite matter if R2 is globally compact. We just want it to be locally compact so that we can perform calculus at those locally compact intervals. So yeah, I know this is a very heavy lecture, but think of it as like a sort of return gift after my 10 days of hiatus. I don't know why I had a hiatus. I just sort of felt lazy, I guess, and I stayed at home last week. So yeah, I'm gonna end the footnote here. Yeah, so this is our FR-Manifold, or Femboy Riemannian Manifold.